GMP is the Erdős-Rényi binomial random graph. This is a clique on R vertices, and I'm asking what's the probability that this doesn't appear as a subgraph of my random graph. Some other types of similar questions of a similar flavor. We could ask, what is the probability that, let's say, a p-random subset of, let's say, the integers 1 up to n contains no k-term arithmetic progression, which I'll abbreviate as KAP, free. Or you could ask, a p-random subset of some group is sum-free. Let's say of maybe Zn is sum-free. So a lot of you will notice or be very familiar that these all fall within the same framework of independent sets and hypergraphs. And indeed, that's the kind of level we're working on today. But when I'm actually going to focus on this first question, and in fact, I'm just going to focus on it for a triangle, just so we can have something concrete to look at, and I can show you some results. But when I show you the proofs of the results, it'll be completely clear how we can deal with all of these questions. I should say I've written lower tails here. These are rather extreme lower tails, where I'm just forbidding the structure completely. I'm saying I don't want any clique. I could be a little bit more mild and say, maybe I just have fewer copies than expected. So maybe 1% of the expected number of copies. And I've written GNP here. It's also a very natural question to ask the same question for GNM. So I'll just write same Qs for GNM, etc. So again, I'll focus on this simple scenario and maybe say a few words at the end how you can deal with this more general case, where you're sort of asking for general low tails or how it adapts to GNM. OK, great. So let's think about the probability that GMP is triangle-free. OK, let me just say a couple of things that are known here. So I'm going to state a theorem. And this is a concatenation of results by Jenssen, Vucak, and Ruchinsky from around 88, and Vucak from 2000. That says the following. So if P is little o 1 over root n, so much, much smaller than 1 over root n, then we know the logarithmic asymptotics of this probability. So the log of the probability that G and P contains no triangle, this is asymptotically equal to minus n choose 3 p cubed. Okay, I'll come back to where this formula comes from, but let me complete the statement. Oh, and by the way, so this is the sort of level of accuracy I'm interested in today about my probabilities. I want to determine the log of probabilities up to leading order asymptotics, or determining the rate function, if you like, of this probability. So this is Jenssen, Vucak, and Ruchinsky. It's sort of the first application of Jensen's inequality that you might have seen in a probabilistic combinatorics course. The second half of the theorem is due to Vucak. It's a bit more tricky to prove. It says if P is much, much bigger than 1 over root n, then we can also determine this rate function. It's asymptotically equal to n squared over 4 log 1 minus p. So Vucak proved this using sparse regularity methods. It can now be proved a lot more simply using the hypergraph container method. So two very, very different approaches to prove these two halves of the theorem. Just briefly, where do these formulae come from? How should you think of them? So this is sort of saying, I'll just do a sort of scribble over here. Imagine sort of the appearance of triangles were all independent. So what's the probability I don't have a single triangle? It's 1 minus p cubed. And if all of these appearances were independent, then I don't see any of them with this probability. And so that's where this guy is coming from. And you should think of these as sort of coming from disordered graphs. They have no particular structure whatsoever, so maybe they look like something like this. Okay. This comes from a very different construction. This is saying, why don't you just be bipartite? Okay, so what's the probability of being bipartite? Well, let me fix a bipartition. And I just say, I don't want any edges in here, and I don't want any edges in here. And that occurs if it's a balanced bipartition, n over 2, n over 2, say. And there's roughly n squared over 4 edges inside here. So, and I'm allowed edges going across. So this is where this comes from. So this is coming from a bipartite construction. It's a very sharp change in structure. OK. So you'll notice this sort of leaves a little gap, and that's sort of where I want to zoom in today in my talk and ask, what if P is in this window? Let's say it's C over root n, where C is some fixed constant. I'll call this the critical window, and I'll justify the name in a second, or in a few slides' time. But let me just mention this same gap between these two methods where sort of Jenssen-type approaches apply and hypergraph container methods apply. The same gap appears in all these questions over here. OK. And so we asked, how can we start to investigate this? What happens inside the critical window? I should say something is known about this. Jenssen inequality applies here too. What does it tell you? It says that this probability is of the order, so capital theta, so equal up to some constants, n to the 3 halves.